just learnt how to perform a specific operation on the device that we intend to use. Let us move on to understand how to customize tf.keras sequential API. There are customization opportunities in model, in writing a new loss function, or training loop, or using a new metric for measuring the performance of the model. Let us learn how to carry out this customization in this section. We will first study how to write custom layers. As you know, layer provides high level abstraction for implementing machine learning models. Many machine learning models are expressed as composition and stacking of relatively simple layers. TensorFlow provides both a set of many common layers as well as easy ways to write your own application specific layer either from scratch or as a composition of existing layers. We have already used layers in various machine learning operations. These are typical statement that we have seen many times in this course. So, this particular statement defines a dense layer with 100 units. We can also specify sometimes the input shape along with the number of units in the layer. So, there are layers like dense layer, which is a fully connected layer, or Con 2D layer, or LSTM, batch normalization, dropout, and many other layers are already defined by Keras. In order to use layer, we simply call layer something like this. Here we call layer with a tensor, which is a matrix, which is 10 cross 5 matrix of zeros. Layers have many useful methods. We can inspect all variables in the layer using tf.variables. A trainable variables can be checked using layer.trainable_variable. The variables have weights and biases. You can see that there are variables over here and biases. So, we have a variable tensor that has shape of 5 cross 10 and we have 10 biases. We can also access variables separately. For example, all the variables can be accessed using layer.kernel and biases can be accessed with layers with layer.bias. We can see that we get the same output. Here the difference is that here we use variables which give us both kernel as well as bias, and we can separately ask for kernel and bias using dot kernel and dot bias accessors. We can also implement our custom layer. In order to implement custom layer, we extend tf.keras.layers class and we implement the constructor, we implement build and a call function. The call function does the forward computations. So, in order to give you an example, a unit in a dense layer takes input. So, essentially it does two operations, one is linear combination followed by nonlinear activation. So, this is an example of a forward computation which is done in the call method. We do not have to wait until build is called to create variables, we can also create them in the constructor. However, advantage of creating them in build is that it enables late variable creation based on the shape of input that layer will operate on. On the other hand, creating variables in the constructor would mean that shape required to create the variable will have to be specified explicitly. So, in this particular case we are defining my dense layer which extends the layer class, and you can see that we have implemented three methods. One is the constructor. In constructor we first call the constructor of the base class, we specify the number of outputs with a variable num underscore outputs. Then in the build stage we specified the kernel, and in kernel we have added weights in the kernel which has the desired shape, and in the call we simply perform matrix multiplication of the input with the kernel or the weight vector. Here we define my dense layer with 10 units, we pass the input shape of 10 cross 5 to the layer. Let us print the layer and the trainable variables. So, you can see that the layer was called with input shape of 10 cross 10, and you can see that you have variable tensor which is a 5 cross 10 tensor, as you can see with layer dot trainable underscore variables, as we can obtain by calling trainable underscore variables method or trainable underscore variable accessor on layer. Having defined the custom layer, the next opportunity for customization lies in defining our own training loop. As you will remember from the earlier classes, the main operation in training is to calculate the gradient and perform parameter update based on the gradient value. Usually these gradients are hand calculated, but TensorFlow provides a way to automatically calculate these gradients based on the forward computation. TensorFlow provides tf.gradient_tape API for automatic differentiation. It computes the gradients of computation with respect to its own variable. TensorFlow records all the operations executed in the context of tf.gradient_tape onto a tape, and then it uses that tape and the gradients associated with each recorded operation to compute the gradients of a recorded computation using reverse mode differentiation. Let us take an example of how this particular thing operates. So, let us say we have x is equal to 3, y is equal to x square and z is equal to y plus 3. Let us use computation graph to represent the relationship between x, y and z. So, we have x is equal to 3, we perform the operation, we raise the power of 2 and we get y, and we add another number to this to get z. Now, what happens is, when you are performing this computation, this is called a forward computation. So, this is a computation graph corresponding to the relationship between 3 variables x, y and z. We perform forward computation. In the forward computation, what we do is, we pass the values of the variable through this particular graph to obtain the value of z. So, concretely, in this graph, we set x to 3, we raise the power of the value of x by 2, we get the output of 9 over here. We add this 9 and 3 to get 12 at z. Now, in machine learning, we are interested in calculating the derivative of the loss that we normally see in the final step of neural network with respect to each of the input variables. So, we are modeling that particular situation with this toy example. In the context of this example, we are interested in finding derivative of z with respect to x, and in order to calculate this particular derivative, we use the chain rule of derivative, where we will take derivative of z with respect to y, which is known, and derivative of y with respect to x. And with this chain rule of calculus, we calculate derivative of z with respect to x. So, derivative of z with respect to x is calculated as derivative of z with respect to y and derivative of y with respect to x. So, we can now so you can see that this particular derivative is 1, because derivative of y with respect to y is 1 and derivative of constant with respect to y is 0. So, this whole thing is 1, and from this side we get 2x. So, the derivative is 2x. So, at x equal to 3, this value is 6. So, this derivative computation is done in a reverse mode differentiation, where we start with this variable, we calculate the derivative of this with respect to y, and then we calculate derivative of y with respect to x to obtain derivative of z with respect to x. So, this is the backward pass, and we use this reverse mode differentiation to calculate the derivative of z with respect to x. So, gradient step is used to record the forward operations, and then it uses TF dot, then it uses the gradients associated with each recorded operations to compute the gradient of a recorded computation. Let us take a concrete example. We define x to be a variable, and in the context of gradient step we perform two operations. First we raise the power of x by 2 and then we get y as a result, and again we raise the power of y to 2 and we get z. So, here we have the following situation. So, x has got some value, x is equal to 1, y is equal to x square and z is equal to y squared. So, we started with x equal to 1, we raise the power to 2, we get y, we again apply the power operator to get the value of z. Here we get y. So, this is a forward computation, and we can calculate the derivative of the recorded computation with respect to the input variable with reverse mode differentiation. So, in this case dz dx is equal to dz dy into dy dx by the chain rule of probability, and this is of x squared. So, this particular value is 2y and this derivative is 2x. So, y as we know is x squared into 2x. So, this derivative is 4 into x to the power 3. So, you can see that since x is equal to 1, we get dz dx to be 4 and dz dy to be 2. So, since x is equal to 1, dz dx is equal to 4x cube is equal to 4 into 1 to the power 3 is equal to 4, and dz dy is equal to 2y and y is equal to x squared, which is 2 into 1 squared is equal to 2. So, dz dx is 4 and dz dy is 2. Let us run this to verify. You can see that dz dx is 4 and dz dy is 2. So, note that here x was defined as a variable. We can also request a gradient from a tensor to another tensor. Let us look at a concrete example. Here x is a tensor and we raise the power of x by 2 to get y, and now we are interested in calculating derivative of y with respect to x. Note that x is a tensor and y is also a tensor. Now, since you are interested in calculating derivative of y with respect to x, which is tensor, we add tape.watch and add tensor x to the watch list. By doing this, we are able to calculate the derivative of y with respect to x with the gradient tape, and we perform both these operations in the context of gradient tape and then calculate the gradient using tape.gradient method. Let us run it and check it out. And you know that this is x square, so derivative will be 2x and x is equal to 1, that is why the value that we see here is 2. So, by default the resources held by gradient tape are released as soon as the gradient tape dot gradient method is called. To compute multiple gradients over the same computation, we create a persistent gradient tape. This allows multiple calls to the gradient method as resources are released when the tape object is garbage collected. Let us look at the example of using a persistent tape. So, we simply add persistent equal to true to gradient tape method and then perform the forward computation in the context of this persistent gradient tape. Since we are interested in calculating derivative of z and y with respect to x, which is a tensor, we first add the tensor x to the watch list and then perform the remaining forward operations. So, here we obtain y by multiplying x to itself, or in other words by squaring the value of x, and z is obtained by squaring the value of y. Let us look at what is the gradient at x is equal to 3. So, we know that we calculated the gradient of z with respect to x is 4x cube. So, that is why at value of x is equal to 3, x cube is 27 and 27 into 4 gets us 108 as the value of gradient. We know that the gradient of y with respect to x is essentially 2x, that is why at x equal to 3 we get the value of 6. Let us print all the 3 gradients, which is the derivative of y with respect to x, derivative of z with respect to y, and derivative of z with respect to x. And finally, we delete the reference to the tape using del command. So, we obtained result as per our expectation. We can also record forward operations even in the presence of the Python control statements or loops. So, this is an example where we first define a tensor containing value 2, and then we define a function called grad. The grad function essentially defines couple of forward computation in the context of gradient tape, and the computation that we carry out is defined in function f, and what f does is f runs the computation in a loop that repeats y times, and if the value of y and then if the value of I is greater than 1 and less than 5, it performs the multiplication operation. It multiplies the output with x. The gradient tape can also be used in the presence of loops or control statements. We can also use operations inside gradient tape to calculate higher order gradients. In this case, we are defining a nested gradient tap. So, there is an outer gradient tap in the context of which there is another gradient tap, and in the context of both these gradient taps we are performing x cube operation to obtain the value of y. In the context of inner gradient tap, we can get derivative of y with respect to x, and in the context of outer gradient tap we can calculate the second derivative of y with respect to x. So far we studied how to use specific devices to carry out TensorFlow operations. Then we studied how to write custom layers, and we also studied how to perform automatic differentiation to obtain gradients of loss functions with respect to input variables through automatic differentiation. With these three concepts, we have some tools available to us for writing custom machine learning algorithms. Let us learn the concepts that we learnt in automatic differentiation to write our custom training loop. Here we will train TensorFlow model from first principles. So, we use variables for storing weights of TensorFlow model, and we use functions like assign, and then we use functions like assign to assign values to the variable. In this case, we are assigning the value of 3 to variable v, and here we are assigning the value of square of v to v itself. So, let us run this particular code. You can see that the value of v was initialized to 1 here, then we assigned value of 3, and here we assign value of 9 to v. And note that we are using v.numpy function to obtain the value present in the tensor. What we will do is we will define a linear model using the concepts that we have learned so far. The concepts that we learned so far are tensors, the variables, and the gradient tap. What are the typical steps involved in this? I would encourage you to pause a video for a minute and recall what we studied in the beginning of the course. So, there are 4 different steps. One is we have to define the model, then loss function, then obtain the training data and train the model. And how do we train the model? We use a specific optimization algorithm for training the model. So, here in linear regression we have model which is a linear combination of weights and the input, and of course we add a bias term to it. So, it x into w plus b, it has got 2 variables, one is w itself and bias. So, what we will do is we will first obtain synthetic data with w equal to 2 and b equal to 2. We obtain a synthetic data that has the value of w set to 3 and value of b set to 2. We will define a simple class to encapsulate the variables and the computations. So, in the constructor we define variables w and b, and we have set them to 5 and 0. In real life or in practice we randomly initialize these values, but for the sake of simplicity in this example we have set these variables to some fixed numbers. And in the call method we are performing the forward computation, where we are multiplying the input by the weights and adding the bias term to it. So, we have a model over here. So, for value 3 we get value, for input 3 we get output of 15. We can see it here, the value of W is 5, x is equal to 3. So, 5 into 3 is 15 and bias is 0. So, 15 plus 0 is 15, that is how we get the value of 15 when we pass 3 as the input to the model. The next task is to define a loss function. Here we use standard L2 loss or a least square error, and the way we define the least square error is we calculate the square of difference between the predicted value and the actual value, and we sum up this difference across all the points in the training data, and this is how we define our loss function. The next step is to obtain the training data. Here we synthetically generate our training data by setting W to 3 and B to 2, and we generate 1000 examples by adding some noise to the regression calculation. So, here we first define input, which is drawn from a normal distribution, and then we have a noise which is again drawn randomly from a normal distribution, and we obtain output by multiplying input by the true weight, add true bias to it and add noise to it, that gives us output. So, let us run these steps. Let us define the model, let us define the loss, let us generate the training data, and let us visualize the training data before building the model. So, you can see that for the chosen parameter values we have loss of 9.01, and you can see that the points in the training that we generated are in blue, whereas the red line or the points represented with red lines are the predicted points. Having obtained the training data, the next step is to train the model itself. Let us define our custom training rule. We are going to use gradient descent to update the weights. Normally in real life applications or examples that we have seen so far, we use tf.train.optimizer, one of the optimizers from tf.train.optimizer. Gradient descent itself is available in the standard Keras package, but here we want to train the model from first principles. So, we will be using gradient step to calculate the derivative of loss function with respect to the input variables. Let us see how do we do that. So, we calculate the loss in the context of a gradient step. So, since we calculate loss in the context of the gradient step, it records all the operation in the forward computation, and when we call a gradient method on the step, it gives us the gradients. For example, here we have gradients of loss with respect to W and B. Having calculated gradient, you must be remembering we update value of W, W new is set to W old minus learning rate times learning rate times the gradient of the loss function with respect to the variables. So, this particular part we get from the gradient TEP. We call the gradient method on the TEP to obtain this particular part. So, this we get and for B you have B new is equal to B old minus which is B old dB. So, we assign W by subtracting W from learning rate into the gradient, and we obtain nu B by subtracting B from learning rate into the gradient with respect to B. This is how we define our training loop, this is how we define the basic training operation. We have to run this function repeatedly. We output the value of W, B and value of current loss. Finally, we also plot how W and B changed and also plot the true value of W and B. Let us run this and experience it. You can see that after training for 10 epochs, so we started W at 5, B as 0, and after 10 epochs both W and B are getting closer to the actual value of W and B. Isn't it cool that we trained our model from first principles? Here we define our own model, we also defined our own training loop, and then we also implemented the gradient calculation using gradient TEP. As a next step, I would strongly encourage you to go through this iris flower classification notebook for end-to-end ML process understanding in the context of customization. So, in this session we learned a number of concepts that will help us in customizing the TensorFlow functionality. We started with how to force operations on accelerated devices, how to write custom layers, how to perform automatic differentiation using gradient TEPs, and we use the concepts learnt in automatic differentiation to define our own custom training. Hope you had fun learning these concepts. In the next class, we will look at some more ways of customizing TensorFlow. See you then. Dhanyavad.